What if a machine could think, feel, or even dream? What if the tools we built to serve us eventually surpassed us, not just in strength or speed, but in intelligence? These questions aren't science fiction anymore. They echo through the headlines, the tech conferences, and even our daily lives. From AI writing your emails to algorithms predicting stock markets, artificial intelligence has become one of the most transformative forces of our time. But where did it all begin? To understand where AI is going and why some people fear it while others worship it, we have to go back, not just to Silicon Valley or the labs of MIT, but to ancient Greece, to medieval philosophy, and to the early days of computation when machines were only a dream. This is the story of how humanity has long imagined intelligence outside itself, and how piece by piece that imagination turned into code. In this video, we'll trace the journey of AI from its mythical and philosophical origins, through its humble beginnings as simple programs, all the way to today's powerful generative models like ChatGPT. Along the way, we'll meet the thinkers, breakthroughs, and setbacks that shape the field. But keep watching, because this is only part one. By the end of this video, you'll see just how close we might be to the next step. An intelligence that's not just artificial, but possibly superhuman. Long before the first line of code was ever written, long before electricity or silicon chips, humanity was already dreaming of artificial intelligence. The idea that lifeless objects could be imbued with thought, personality, or even consciousness is not new. In fact, it's ancient. And to understand today's AI, its promises and its dangers, we must begin where all deep ideas begin. In myth and philosophy, let's rewind the clock a few thousand years to ancient Greece. In the myth of Talos, the gods forged a giant bronze man to guard the island of Crete. He could patrol the shores, hurl boulders at invaders, and even bleed ichor, the blood of the gods. He wasn't human. He wasn't alive in the biological sense. But he was intelligent, artificial. Sounds familiar? Ancient myths across cultures, Greek, Egyptian, Chinese, are filled with stories of mechanical servants, talking statues, and enchanted artifacts. They weren't just tales of magic. They reflected a fascination with the possibility that intelligence could exist beyond the human form. That very idea still drives us today. But myth alone wasn't enough. As philosophy matured, thinkers began to dissect the nature of the mind. In the 4th century BCE, Aristotle described the brain not as a source of thoughts, but as a cooling mechanism for the blood, an idea later disproven, of course. Yet, he also gave us something vital: the foundations of formal logic. His work on syllogisms, if A equals B and B equals C, then A equals C, laid the groundwork for computational reasoning. It was the first attempt to mechanize thought. Fast forward to the Islamic Golden Age. The Persian polymath al-Khwarizmi, whose name gave us the word algorithm, developed methods of problem solving that were so systematic, they still form the basis of modern computing. Think about that. Over 1,000 years ago, algorithms, those sequences of instructions we now feed into machines, were already taking shape. Then came the Enlightenment, and with it, a revolution in rational thought. In the 17th century, René Descartes proposed that humans were divided into two substances, the physical body and the thinking mind, the res cogitans. This dualism led to provocative questions. Could a machine ever possess a mind? Could thought arise from matter alone? Descartes doubted it, but others were more optimistic. German philosopher and mathematician Gottfried Wilhelm Leibniz imagined a universal language of reasoning, what he called the characteristica universalis, where logic could be reduced to symbols and rules. He even imagined a device that could compute answers from logical premises. "Let us calculate," he said, suggesting that disputes could one day be resolved not through argument, but through computation. Sound familiar? That dream is still alive in modern AI models trained to resolve problems, generate ideas, and interpret language. By the 19th century, these abstract dreams were becoming concrete. Charles Babbage designed the first mechanical computer, the analytical engine, and Ada Lovelace, often considered the world's first programmer, recognized its potential to go beyond numbers. She envisioned a machine that could manipulate symbols, generate music, and perhaps even imitate the human brain. It was a turning point. For the first time, humanity wasn't just dreaming of intelligent machines, it was trying to build them. But even then, deep philosophical questions lingered. What is intelligence, really? Is it the ability to calculate, to reason, to feel? If we replicate those abilities in a machine, is it truly intelligent, or just a sophisticated illusion? These aren't just academic questions. They're central to how we define AI today and to the future we're racing toward. The origins of artificial intelligence didn't begin with chips or servers. They began with imagination, with the human desire to understand itself by building something in its own image. A mind made of metal, a soul made of software. And in that pursuit, we've never stopped asking, can we create something that thinks like us, or even beyond us? And as we move from myths and philosophy into the era of real machines and mathematical logic, that question becomes more urgent. Because while the past was full of dreamers, the next part of our story is full of doers, people who turned philosophy into function, logic into language, thought into code. By the end of the 19th century, the world was standing on the edge of something monumental. The dreams of myth and the abstractions of philosophy were beginning to crystallize into something real, something mechanical, logical, and soon, digital. The groundwork was being laid not with wires or electricity, but with ideas, revolutionary ideas that would form the backbone of artificial intelligence. At the heart of this transformation was mathematics. In the 1800s, British mathematician George Boole asked a powerful question. What if logic could be expressed as mathematics? In his book, The Laws of Thought, Boole introduced what we now call Boolean algebra, a system where logical statements could be reduced to combinations of true and false, or 1 and 0. It was a radical shift. Thought itself, in all its complexity, could be reduced to binary operations. Today, Boolean logic powers every computer, every algorithm, every AI model. But back then, it was more of a philosophical curiosity than a practical tool. That would change soon. Meanwhile, Charles Babbage, whom we met briefly in the last chapter, was building something no one had ever seen before, the analytical engine. Though never completed in his lifetime, the design included many features of a modern computer, an arithmetic unit, control flow with loops and conditionals, and memory storage. Babbage didn't just dream of a machine that could crunch numbers. He wanted a device that could follow instructions, repeat tasks, make decisions. And then came Ada Lovelace. Often overlooked in her time, Lovelace saw what even Babbage didn't. She understood that the analytical engine could do more than just calculate. It could manipulate symbols. In 1843, she wrote the first algorithm intended to be processed by a machine, making her the world's first programmer. More importantly, she imagined a future where machines could create art, compose music, and explore ideas in ways that mimic the human mind. A full century before the invention of the modern computer, Ada Lovelace was already predicting something like artificial intelligence. But the final puzzle piece came in the 20th century, with a young British mathematician named Alan Turing. In 1936, Turing published a paper that would become one of the most important in the history of science. In it, he introduced the idea of a hypothetical machine, a universal machine, that could simulate any computation given the right instructions. This wasn't just a theoretical device, it was a blueprint for a programmable computer. What Turing showed was simple but profound. If a task can be logically described, then a machine can be built to perform it. This became the foundation of computer science. Turing didn't stop there. During World War II, he played a key role in breaking the Nazi Enigma code using early electromechanical computers. His work didn't just save millions of lives, it proved that machines could do things once thought impossible for anything other than a human mind. This single question would echo through decades of AI research, ethics debates, and sci-fi stories. Even today, as people talk to models like ChatGPT or AI-powered virtual assistants, they're engaging, knowingly or not, with Turing's legacy. Turing's brilliance came with a tragic ending. Persecuted for his identity and largely unrecognized in his lifetime, he died in 1954 at just 41. But his ideas lived on, quietly seeding the explosive growth of computing and artificial intelligence in the decades that followed. Around the same time, other mathematicians and logicians were making crucial contributions. Kurt Gödel showed that even in formal logical systems, some truths are unprovable, a humbling reminder that logic has limits. Claude Shannon, the father of information theory, showed how to transmit and store data efficiently, laying the groundwork for digital communication and machine learning. By the mid-20th century, the philosophical dreams of centuries were colliding with raw technological capability. Circuits replaced cogs, algorithms replaced legends, and suddenly the world was no longer just imagining artificial minds, it was building them. This period, the birth of computation, was a turning point. For the first time in history, we had the tools to make thinking machines possible. But possibility is not the same as reality. That came next. In the following section, we'll enter the post-war era, a time of bold experiments, groundbreaking discoveries, and perhaps the most important conference you've never heard of, the moment when artificial intelligence became a field of science. And as we continue tracing this path, keep this in mind. Every time you ask your phone a question, every time an AI recommends what to watch or write, it all goes back to these moments. The birth of logic, the rise of machines, and a handful of thinkers who dared to ask, what if intelligence could be engineered? By the 1950s, the pieces were in place. The math had matured. The logic had been formalized. The machines, massive, humming, room-sized behemoths, were ready to be programmed. The stage was set, and humanity stood on the brink of something extraordinary, the moment artificial intelligence stepped from theory into practice. It began, like many revolutions, with a conference. In the summer of 1956, a group of young scientists gathered at Dartmouth College in New Hampshire for what would become the most important meeting in the history of AI. The invitation was bold. It declared, every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. Think about that. Not just logic, not just math, but intelligence itself, modeled, coded, mechanized. Among those present were some of the most brilliant minds of their time. John McCarthy, who coined the term artificial intelligence. Marvin Minsky, a visionary who would later co-found MIT's AI lab. Claude Shannon, the father of information theory. And Herbert Simon and Alan Newell, pioneers of cognitive simulation. They weren't just theorizing, they were planning a revolution. And they were optimistic, extremely optimistic. In the years that followed, AI entered what many would call its golden age of ambition. Researchers believed that human-level intelligence was just around the corner, maybe a few decades away. Computers had just started to play chess, solve algebra problems, and prove logical theorems. It felt like anything was possible. One of the earliest breakthroughs came from Newell and Simon, who developed a program called Logic Theorist in 1955. It was designed to mimic the problem-solving skills of a human mathematician. Not only did it prove over 30 theorems from Principia Mathematica, it even found a proof that was more elegant than the original. This wasn't just number crunching, this was symbolic reasoning. Next came ELIZA, developed by Joseph Weizenbaum in 1966. It simulated a Rogerian psychotherapist responding with canned phrases like, "Tell me more about that," or "How do you feel about your father?" It was primitive by today's standards, but people were stunned. Some even confided deeply personal thoughts to Eliza, convinced they were speaking to something intelligent. But not all experiments were so mechanical. Terry Winograd's SHRDLU, developed at MIT, allowed users to interact with a virtual world of blocks using natural language. You could type, "Put the red block on the green cube," and it would do it. It understood context, syntax, and even simple reasoning. For the first time, machines weren't just calculating, they were understanding, or so it seemed. In those days, AI research split into two camps: symbolic AI and connectionism. Symbolic AI, sometimes called good old-fashioned AI, focused on rules, logic, and explicitly programmed knowledge. It treated intelligence as a puzzle to be solved with structure and syntax. Connectionism, on the other hand, was the early seed of neural networks, systems inspired by the human brain, built from layers of simple units that learned from experience rather than being explicitly taught. But in the 1960s, neural networks were still in their infancy, struggling with limitations in computing power and data. Despite these differences, the optimism was contagious. Governments and universities poured money into AI research. Computers were finally fast enough to handle complex programs. The idea of machine learning, expert systems, and intelligent agents took root. But underneath all the excitement, a tension was building. As impressive as early systems were, they lacked flexibility. Eliza couldn't hold a real conversation. Shudlu couldn't function outside its tiny world of blocks. These programs weren't general thinkers. They were impressive illusions, proofs of concept, not consciousness. Still, something profound had changed. AI was no longer a myth or a philosophical toy. It was a field of science, a discipline with its own rules, goals, and legends. The dream of artificial intelligence had officially begun. And as the 1960s came to a close, the world began to wonder, what would happen when machines became not just smart, but smarter than us? That question would come crashing down in the decades to follow, as AI faced its first major reckoning. The hype had run ahead of the hardware, promises were made that couldn't be kept, and soon the winter winds would begin to blow. But we're getting ahead of ourselves. For now, imagine being there, at the birth of a new kind of intelligence, standing in a lab at MIT or walking through a research center at Stanford, watching a computer respond in natural language for the first time, hearing the punch cards clatter as a machine proves a theorem you didn't even think it could understand. It felt like magic. It felt like destiny. And even though the road ahead would be bumpy, the spark had been lit. And from here on out, there was no turning back. Every great revolution faces a moment of disillusionment, a time when the dream feels farther away than ever. For artificial intelligence, that moment came not once, but twice. The 1970s and 1980s saw what researchers now call the AI winters. Two extended periods where excitement froze, funding dried up, and optimism gave way to skepticism. But to understand why, we have to return to the height of the 1960s, when promises were soaring. The early AI pioneers were bold. Some predicted that machines with human-level reasoning would arrive within a generation. Newspapers echoed the hype, governments invested heavily, and researchers made ambitious claims. It felt inevitable. Machines would soon walk, talk, reason, even feel. But then, reality struck. AI systems, as it turned out, were brittle. Programs like Eliza or SHARDLU, while impressive in tightly controlled environments, failed completely when exposed to the messy, unpredictable nature of the real world. Simple tasks that a child could perform, like recognizing a cat or walking across a cluttered room, were nearly impossible for machines. In 1973, a damning report from the British government, called the Lighthill Report, evaluated the state of AI research in the UK. It concluded that AI had failed to live up to its promises and offered little practical value. The result? Massive funding cuts across British universities. And that was just the beginning. In the US, Similar concerns arose. The Defense Advanced Research Projects Agency, DARPA, which had heavily funded AI, grew frustrated with the lack of results. Researchers were requesting millions for projects that rarely delivered beyond narrow laboratory demonstrations. One by one, the money began to vanish. This was the first AI winter, a period of disappointment that chilled the field throughout the 1970s. Many researchers abandoned AI entirely, departments closed, public interest faded. But behind the scenes, some persisted. One area that survived the frost was expert systems. These were rule-based programs designed to mimic the decision-making of a human expert. Instead of trying to replicate general intelligence, expert systems focused on narrow domains: medicine, chemistry, engineering. One of the most famous was mycin, developed at Stanford in the 1970s. It could diagnose bacterial infections and recommend treatments with surprising accuracy, sometimes better than human doctors. Corporations saw promise. In the 1980s, businesses began building their own expert systems to automate decision-making. This sparked a second wave of excitement. By the mid-1980s, AI was back in fashion. Investments surged. Japan launched the ambitious fifth-generation computer systems project, aiming to leap ahead in AI-powered computing. Conferences were packed again. Once-cold labs buzzed with new energy. But there was a catch. Expert systems, though useful, had limitations. They relied on rigid rules, if this, then that, and couldn't learn or adapt. Updating them was a nightmare. Worse, they couldn't cope with uncertainty or incomplete information. As problems became more complex, rule-based systems simply broke down. And once again, expectations outpaced results. By the early 1990s, AI was facing its second winter. The hype had returned, but so had the disappointment. The Japanese fifth-generation project failed to deliver. Funding from private and public sectors shriveled up once more. Skeptics began to ask, was artificial intelligence just a fantasy after all? It was a dark time for the field. And yet, beneath the surface, something was stirring. Out of the spotlight, a small group of researchers had never given up on a different idea. An old one, inspired by the brain itself: neural networks. Back in the 1950s, pioneers like Frank Rosenblatt had experimented with perceptrons, early neural models that could learn simple patterns. But after Marvin Minsky and Seymour Papert published a scathing critique in 1969, the entire approach was abandoned for years. Now, with better algorithms, more data, and slightly more powerful computers, a few brave scientists began to revisit the concept. They introduced backpropagation, a method for training multi-layered networks more effectively. Suddenly, neural networks didn't seem so hopeless, but progress was slow and the mainstream still wasn't convinced. Funding remained scarce. Many researchers risked their careers by pursuing machine learning at all. Still, the spark was returning, and in hidden corners of academia, in tiny research groups, a quiet revolution was taking shape, one that would change the world in ways few could imagine. The AI winters were painful, they were humbling, but they were also necessary. They weeded out the hype, exposed the limits of rule-based thinking, and forced researchers to ask harder, deeper questions about what intelligence truly means. Most of all, they set the stage for something far more powerful: machines that could not only process rules, but learn, adapt, evolve. And as we move into the 1990s and beyond, we'll witness AI's great comeback, a new dawn driven not by promise alone, but by data, computation, and algorithms that could finally learn. But remember, every winter contains the seed of a spring, and for artificial intelligence, the thaw was about to begin. The frost of the AI winters had lingered for decades. Many had given up hope. Funding was scarce, expectations were tempered, and the grand dreams of human-like intelligence had been shelved in favor of more modest ambitions. But beneath the surface, a quiet revolution was beginning, one that would not rely on rigid rules or symbolic reasoning, but on something far more powerful: learning. At the heart of this revolution was a simple yet profound idea. Instead of programming a machine to know, we could train it to learn. This was the birth of machine learning, a shift from hand-coded logic to systems that could identify patterns in data, improve through experience, and generalize to new situations. The difference was subtle, but transformative. Intelligence was no longer about knowing all the rules. It was about extracting structure from noise. One of the first sparks came from an old idea revisited with fresh tools: neural networks. Thanks to improved algorithms like backpropagation, introduced in the late 1980s and refined in the 1990s, researchers could now train deeper, more complex networks. These models mimicked the structure of the human brain, layers of artificial neurons connected by weights that adjusted through training. For the first time in years, machines began showing genuine adaptability. Yet early neural nets had limitations. They worked best in small domains and often struggled to scale. So during the 1990s and early 2000s, another machine learning approach took center stage: support vector machines, decision trees, and Bayesian networks, algorithms rooted in statistics, optimization, and probability. These models powered spam filters, fraud detection, and medical diagnostics. AI was becoming useful again, quietly, practically, and reliably. But the true breakthrough, the one that would change the course of history, was still brewing in the background. Meanwhile, one event in 1997 captured global attention. IBM's Deep Blue defeated world chess champion Garry Kasparov. It was the first time a reigning world champion lost a match to a computer under standard chess tournament conditions. To many, it was a symbolic moment. The machine had conquered a game long considered the pinnacle of human strategy. But Deep Blue wasn't intelligent in the way people imagined. It didn't learn from experience. It used brute force search, evaluating millions of positions per second. It was impressive, but narrow. Real intelligence, the kind that could adapt, evolve, and understand, was still elusive. Enter the internet. In the early 2000s, something changed. Data exploded. The rise of the web, smartphones, and social media created a digital tsunami. Billions of photos, messages, clicks, and videos generated every day. For machine learning, this was gold. After all, learning systems need one thing above all else: examples. Suddenly, we had more data than ever before. But data alone wasn't enough. We also needed the computational power to process it. Fortunately, that arrived too, thanks to advances in graphics processing units, GPUs. Originally designed for rendering video games, GPUs turned out to be perfect for training large neural networks. And with that, the long-dormant dream of deep learning was reborn. In 2012, everything changed. A team from the University of Toronto, led by Geoffrey Hinton, unveiled a deep neural network called AlexNet at the ImageNet competition. A challenge to build models that could classify images across thousands of categories. AlexNet didn't just win. It crushed the competition, reducing the error rate by nearly half. It was a watershed moment. Overnight, deep learning exploded. Suddenly, neural networks were outperforming traditional models in speech recognition, image analysis, translation, and more. Companies took notice. Google, Facebook, Microsoft, Amazon, they all raced to build AI labs and hire top talent. AI was no longer a dusty academic pursuit. It was a global arms race. Soon, machines were generating realistic speech, translating languages with near-human fluency, identifying objects in photos with superhuman accuracy, and even writing basic news articles. AI began creeping into everyday life, hidden inside your phone's keyboard, your car's navigation system, your search engine, your Netflix recommendations. But something deeper was happening too. AI was no longer just following rules or recognizing patterns. It was beginning to model language, the very essence of human thought. Early natural language processing, NLP systems, relied on statistical tricks. But with deep learning, language models became richer, more nuanced. Word embeddings like Word2Vec and Glove allowed machines to capture relationships between words in complex, multidimensional space. And in the late 2010s, a new architecture would change everything again. Transformers. Introduced in 2017 in a paper titled "Attention is All You Need," the transformer model revolutionized language understanding. By focusing on the relationships between words, no matter how far apart, they enabled models to understand context, syntax, and meaning at an unprecedented scale. The stage was set, the tools were ready, the data was abundant. Something extraordinary was coming. The dream of AI, once buried by winters, revived by learning, and supercharged by data, was about to take its most stunning leap yet. And in the next chapter, we'll witness that leap firsthand, from the rise of transformer-based models to the arrival of ChatGPT, DALL-E, AlphaFold, and beyond. But as these machines grow more powerful, more fluent, more human in their behavior, we must ask, what happens when the line between human and machine begins to blur? For decades, artificial intelligence had crawled forward, step by careful step, through rules, logic, learning, and data. But in 2017, something happened that felt less like a step and more like a quantum leap. A quiet research paper from Google, titled "Attention is All You Need," introduced a strange new architecture called the transformer. It didn't look like anything before it. It didn't rely on recurrency or convolutions. Instead, it used a mechanism called self-attention, allowing it to weigh and compare every word in a sentence to every other word, all at once. No one knew it at the time, but this paper would become the cornerstone of a new AI era. Transformers weren't just fast, they were astonishingly powerful. They could understand language in ways no previous model ever could. They could translate between languages, summarize articles, answer questions, and even generate human-like text. And perhaps most importantly, they scaled massively. The more data you gave them, the bigger you built them, the better they performed. That simple truth led to a new philosophy in AI research. Scale is all you need. Soon, the race began. In 2018, Google released BERT, a transformer-based model pre-trained on massive text corpora and fine-tuned for dozens of natural language tasks. It marked a turning point. Instead of training a new model for every job, you could train one foundation model and then adapt it for anything. But BERT was just the beginning. At OpenAI, researchers were quietly building something larger. In 2020, they unveiled GPT-3, a 175 billion parameter language model trained on vast swaths of the internet. It could write essays, poems, code, dialogue, and jokes. It could explain physics, simulate personalities, and mimic almost any writing style with uncanny fluency. The world watched in awe. Was this the moment AI became creative? GPT-3 was followed by DALL-E, which could generate original images from text prompts, a cat dressed like Napoleon, a floating city made of glass. It didn't just understand language, it translated words into visuals. Then came Codex, which turned plain English into working code, giving birth to tools like GitHub Copilot. AI was no longer an academic curiosity, it was a commercial explosion. And yet, for all their power, these models weren't taught in the traditional sense. They weren't hand-coded experts. They were trained on raw data, billions of words, images, conversations, and allowed to discover patterns on their own. They weren't programmed to follow logic. They learned to imitate the world. This shift was profound. In the old days, intelligence was modeled top-down, rules first, behavior second. But now with transformers and foundation models, we were seeing bottom-up emergence, complex behavior arising from simple training at scale. It raised a new question. Are we building machines that understand, or machines that predict? Because make no mistake, these models don't think in the human sense. They don't feel, or reason, or comprehend. But they are astonishing predictors. Given a prompt, they can generate the most statistically likely next word, pixel, or line of code. And at scale, That ability creates the illusion of thought, but illusions are powerful. ChatGPT, released in late 2022, brought this illusion to the masses. Trained on GPT 3.5 and later GPT-4, it became the first widely used conversational AI that felt real. Not just smart, but helpful, articulate, and strangely human. Students used it to study. Writers used it to brainstorm. Programmers used it to code. And behind the curtain, models kept growing. Anthropic's Claude, Google's Gemini, Meta's Llama, Mistral, XAI, Cohere, Inflection. A new wave of labs, models, and breakthroughs surged forward, all built on the transformer backbone. They analyzed genomes, created art, wrote music, composed legal briefs, and predicted protein structures. AI was no longer a tool, it was becoming an infrastructure. But something deeper was stirring too. As these systems grew more capable, researchers began noticing strange behaviors, emergent abilities that hadn't been explicitly trained. Models could do basic arithmetic, reason over long contexts, or answer riddles they'd never seen. Some even showed signs of theory of mind, the ability to model what another person is thinking. It was eerie, unexpected, and impossible to ignore. The more we scaled, the more the models behaved in ways we didn't fully understand. This was the beginning of a new kind of intelligence. Not logical, not emotional, not even biological, but statistical, general purpose, and disturbingly open-ended. We call these systems foundation models because they're not built for one task. They're built for any task. They can be adapted for law, medicine, cryptoanalysis, climate modeling, filmmaking, and more. A single model, trained once, becomes 1,000 tools. And this raises a deeper question, one we'll explore in the next episode. If AI keeps scaling, if we keep feeding it more data, more compute, more memory, when exactly do we cross the line from tool to mind? Are we approaching the dawn of AGI, artificial general intelligence? Or perhaps something even more alien, superintelligence? The transformer was just the ignition spark. What it powers next could change everything. From ancient myths of mechanical servants to the cold circuits of modern neural networks, the dream of artificial intelligence has always been a mirror, reflecting not just our hopes for machines, but our deepest questions about ourselves. What is thought? What is language? What is creativity, emotion, intelligence? We've watched AI evolve from rigid rule followers to fluid pattern seekers, from brittle logic systems to deep learning models that speak, paint, compose, and assist. We've seen winters of disappointment give way to revolutions in scale, and now we live in an age where AI quietly touches nearly every part of our lives, our phones, our homes, our work, our imagination. But this is not the end of the story. It may not even be the middle. Just beyond the edge of today's technology lies a horizon we are only beginning to glimpse, where models don't just respond, but understand, where they don't just assist, but act, where intelligence itself may become untethered from biology. Are we on the verge of birthing minds, not of flesh and blood, but of code and computation? What happens when we build something smarter than ourselves? And more importantly, how do we control it? The age of deep learning has rewritten the rules, but the next chapter may rewrite reality. In the next episode, we'll dive headfirst into the future, into the promises, perils, and philosophical storms of AGI and superintelligence, because the machines are learning fast, and they're not stopping.